Now, having shown you an interesting application of our change of variable formula, it's time for us to prove our theorem. Our theorem is this theorem. Maybe so I state it here again. Okay, briefly, our theorem is this. Omega single phi is a map C2, okay, such that for parametrization of the boundary of omega, that is the map the composition denoted by Y, the composition is parametrization of the boundary of D, and the F is a C1 function on D. Then our result is that the integral of F over D equal the integral of F and we need a positive and negative sign in front of the integral. The sign, as I mentioned, the sign does not depend on the function f. If for some function f you take positive sign, then for all the other functions you should take positive sign. The sign only depends on the map phi, as we will see in our proof. Okay, so this is our theorem. It's time for us to prove this theorem. Okay, now proof. The map phi is a map from n-dimensional set omega to another n-dimensional set D. Here is D. So it can be expressed component-wise. Assume that phi is given by this map yi equal phi yi depend on x1 xn. Okay, then we take a function p, take a continuously differentiable functions p such that f is the partial derivative of p with respect to y1. Because f is c1, such p exists. You can take such a p, such function p exists. Actually, the p can be given in this way. Py be the integral of, for example, 0 to y1 ft y2 yn dt. Then you can prove that this p satisfies this requirement. The partial derivative with respect to y1 is exactly f. Okay, it is this place we need f to be c1. If f is only continuous, the p might not be c1. Okay, so in this place we need f to be c1, so that this p is also c1. Continuously differentiable. So the function p is given here. It defined over the D, but we can compose the p and our map phi to obtain a new function. That is this function. Obtain this new function p tilde. Okay, so p tilde is the composition of p and phi. So this is a function defined on omega. P is defined on D. Okay. Now, so by our assumption, the composition of phi and x is a parametrization of the boundary of the domain D. It's the parametrization of a surface. Now, once you have a parametrization of a surface, you can write the normal vector. Okay, you can write down the normal vector. Y equal to phi x is parametrization of the boundary of D by our assumption. Okay, our assumption on phi is that once x is a parametrization of the boundary of omega, the composition of phi and x is a parametrization of the boundary of D. Okay, so this is our assumption. So having obtained a parametrization of the boundary, you can write down the normal vector. The normal vector is n equal dy2 yn. We have computed the normal vector for a parametrization surface, parametric surface in our study of differential calculus. So this is the normal vector given by the parametrization. This is the normal vector of the boundary of D given by the parametrization y. Y is a parametrization of the boundary of D. So this is the normal vector. Okay. And the unit normal vector is nu, that is normalized. But our normal vector n might point in inward or outward, we don't know. N might be pointed inward or it can point outward. We don't know. The n computed in this way, using this expression, the resulting n might point inward D or outward D. We don't know. Therefore, to make sure that its normalization to be an outward normal vector, we need a positive or negative sign in front of this normalization. Okay, so this which is the positive and the negative sign in front of this normalization will obtain a unit outward normal vector. Outward unit normal vector. And suppose its component is nu1, nu n. It has n components denoted by nu1, nu n. Okay? Then this is outward unit normal vector of the boundary of D. Okay. Now we take a vector field. Let A to be A1, AN, and the n tilde to be n tilde 1, n tilde n. Here the components are given as follows. AI is -1, I plus 1. Y2, Yn, Jacobian determinant of Y2, Yn with respect to x1, xi missing, xn. This is AI. Here the xi which ahead and writing in blue means that xi is missing. That is, this AI is the -1 to the I plus 1 multiplying the Jacobian determinant of y2, y3, yn with respect to x1, x2, xi minus 1, and then xi plus 1, xi plus 2, and then xn. Xi is missing. Okay, this is AI. This is the ith component of our vector field A. And for the n tilde I is minus 1, I plus 1, multiplying the Jacobian determinant of x1, xi hat also means xi is missing, xn over u1, un minus 1. Okay, so we can using we can construct such two vector field A and n tilde which are given with their component in this way. Okay, using the Jacobian determinant of the corresponding vectors variables to construct their components. So we obtain we define the two vector field. Then you should know that n tilde is normal vector of the boundary of n tilde is normal vector of the boundary of omega. The expression of the components of n tilde tell us that n tilde is precisely the normal vector of the boundary of omega. Okay, this is very important. So the normalization of n tilde denoted by nu tilde. Of course, we don't know whether n tilde point inward or outward. We don't know. So we need to, if it point inward, we need to add a negative sign to obtain the outward normal vector. So which is the proper sign normalizing the n tilde. This is normal vector, unit normal vector of the boundary of omega. Okay, so this is our preparation. Now we want to compute a quantity. The quantity is the first component of nu. The first component of nu, that is nu1. The first component of nu here, nu1 multiplying the norm of capital N. That is the first component of capital N. Okay, so we would like to compute this component, positive or negative, nu1 multiplying the norm of N. This is the first component of the vector N. From the definition of nu, you see that the first component of nu multiplying the norm of capital N, which is the positive negative sign, is precisely the first component of capital N, while the first component of capital N is the Jacobian determinant of y2, yn, with respect to u1, un minus 1. So you see that this is precisely y2, yn, with respect to u1, un minus 1. This quantity is precisely this Jacobian determinant. But how to compute this Jacobian determinant? We know that u is a parameter variable in Rn minus 1 from the set u, and the x is the point in the boundary of omega, and the y is the point on the boundary of d. So y is a function of x, y equal to phi x, x equal to xu. The composition relation is that y equal to phi x, x equal to xu. Okay, so we want to compute the Jacobian determinant of y with respect to u. That is, we need to compute yi xj, uj. We need to compute such partial derivative. Of course, we need to use the chain